everyone, it's Mahathi with Global Climates for our 5th video in the Introductory Earth Sciences series. So today we're going to take a step back from studying the Earth and take a look at the formation of the Earth and the solar system. So this journey starts off a long time ago, more specifically with a big explosion that happened over 13.6 billion years ago, known as the Big Bang. So the Big Bang is considered to be the beginning of our universe, in which this huge explosion released enormous quantities of the gases hydrogen and helium into space. Now, what's important about hydrogen and helium are that they are kind of the fundamental elements that start to build up our universe. And so with the release of these gases, now there are a bunch of, gas clouds that have formed in the universe, and over time, maybe some of these gases have started to come together to form stars. But let's fast forward to the formation of our own solar system. So this process happens about 5 billion years ago. This mechanism is documented by what is called the nebular theory. So this theory essentially proposes the mechanism by which our solar system was formed. All right, so now we have all these gases, the hydrogen, the helium, and some other gases that have started to collect up into these gas clouds. All right, so somewhere in space, in the galaxy called the Milky Way, we have this cloud of gases and dust. And as you may recall, or something you might have learned before, our Earth, for example, is not just made up of hydrogen and helium. It's made up of other elements too. And so the way these other elements formed was in stars. There's a process known as nuclear fusion. We'll go over this. We'll go over this in more detail later on. But in fusion, we actually can take hydrogen and helium, and we can actually create a lot of the other elements. And for the elements that can't be created through fusion, there are other big explosions known as supernovas that can also create these explosions. So back to our cloud of dust, right? So we have, gases and dust particles. And over time, these particles, they're attracted to each other by gravity, and they start to move closer and closer together. And, it's thought that another, for example, a supernova explosion could have also triggered, the condensation of this gas cloud. So basically in this process of condensation, we have these little gas molecules and these little particles, these dust particles coming together. They join together to form larger and larger objects. And so through this process of condensation, temperatures, that starts heating up, and it starts heating up, and as these particles are coming closer together, it becomes more dense, but it also causes this cloud to start to rotate. And so one analogy that is often given and can help you understand this concept is, well, if you are, on ice and you're figure skating, for example, when figure skaters are spinning and they have their arms out and they draw their arms towards their body, it causes them to spin even faster. And so the same process is kind of operating here. As these particles are coming closer and smushing together, this cloud is starting to spin faster and faster. And as it rotates, it almost forms something that's like a disc. It's almost like a disc shape. And at the center, we have a protostar. And so this protostar is kind of the proto-sun. Proto is a root that means beginning, and protostar and proto-sun by extension would mean kind of the early star or the before star. And that's exactly what this is. This is the first step towards the sun being formed. And so now that we have this kind of flat disk, condensation continues to occur. So I mentioned earlier that as these particles started to come together, it started heating up, temperature started to rise, and this is a process known as gravitational heating. But over the next few million years, this process started to slow down a bit, and temperatures, at least in the first in the areas closest to the sun, started to cool down again. And this kind of leads us to the formation of our inner planets. So the formation of the inner planets are the 4 planets that are closest to the sun. So Mercury, Venus, Earth, and Mars. And they start to form as I mentioned, these areas near the sun start to cool. And so as these areas start to cool, it causes all the molecules to start sticking together and forms these smaller objects. Well, we have our sun, right? And these molecules start sticking together to form these smaller objects known as planetesimals. So obviously not to scale here, but we have these planetesimals. So these planetesimals could also be called protoplanets, and it's that same concept where these are the before planets. What the planets were before they actually became planets. And as the gravitational attraction started to pull these molecules together and compact them more, we got our inner planets: Mercury, Venus, Earth, and Mars. And so maybe just And so this is the formation of our innermost planets. And at the same time as these, these inner planets are coming together, we also have the outer planets. So the outer planets are Jupiter, Saturn, Neptune, and Uranus. And so these planets are forming at the same time, except they're even farther out. They're even farther away from the sun than the inner planets are, and so it's much, much colder. And so in these areas, we see a lot of ices. So ices, they're water, carbon dioxide, methane, all these different types of ices. There's also ammonia, because it's so much colder, so we see a lot of these ices. And so when these ices and other rocky and metallic elements came together, they formed the cores of our next few planets: Jupiter, Saturn, Uranus, and Neptune. And so these are much bigger than the inner planets. We'll go over the differences between the inner and outer planets in a future episode, but that's kind of how they come together. And we mentioned earlier how supernova explosions and fusion helped create the other elements, things like oxygen and carbon, from hydrogen and helium. And so one thing that's interesting is nickel and iron came together to form the cores of most of the inner planets. And while there was a lot of nickel and iron in these outer planets as well, they're also so massive that they were able to hold on to some of the lightest elements. So Jupiter and Saturn actually have hydrogen and helium in their atmospheres, whereas, for example, on Earth, we don't have hydrogen in our atmosphere. We have very, very little helium. We have very little helium, and the reason is because they were so light, Earth's gravity could not hold on to them, and so processes such as solar wind, which is emitted by the sun, actually pushed those gases away from our atmosphere. So today we kind of went over a quick review of how our solar system actually formed. This entire journey starts off with the Big Bang that releases these two fundamental blocks for our universe, hydrogen and helium, that then form these gas and dust particles, these gas and dust clouds, and the specific cloud that helped form our solar system is known as the solar nebula. And within the solar nebula, condensation processes led to the formation of this disk-like structure, which would then extend out as more condensation occurred into the disk of our solar system, with the sun at the center, and then our four inner planets, Mercury, Venus, Earth, and Mars, and then our four outer planets, Jupiter, Saturn, Uranus, and Neptune. We even have an asteroid belt in the middle, which is composed of, again, those kind of planetesimals, those protoplanets, right? Because they never fully formed into a planet, so we have a lot of those little mini, conjoined, coalescing elements that created those asteroids. So I hope you all enjoyed today's lesson on the origins of the solar system, and I hope that it was helpful. If you did find it helpful, please subscribe and like this video, and comment down below any suggestions you have for future content and lessons. Thank you all for watching. Bye!